First of all, I'll talk about the hull failures. Here in the picture, you can see a ship from 1943. As you can see, it just break, it broke in the middle section. So first of all, like this failure actually happened because the German U-boats were sinking cargo ships during the World War II, and the Americans were actually looking for a way to build the ships faster than the German U-boats were actually sinking their ships, so that they can have the chance to replace the ships in a shorter time. So they were actually looking for a revolution for the construction, as I said, in a faster and in greater numbers. So they came up with the idea of the all welded ships, and they just welded all the steel sheets, and they tried to make this whole the whole hull with one steel plate that is welded to another, but it actually ended up with catastrophic failures. So the actual reason is the brittle fracture. As we all know, the metals have different characteristics in different temperatures. In higher temperatures, they are more ductile, so they don't break. They can have the plastic deformation, but in the lower temperatures, they are more tend to make the brittle fracture, which is like a glass like breaking. So, as I said, during the World War II, they came up with the idea of all welded ships. They built them, but there were some flaws and like cracks in the structure, and the tensile loading was very high. So, and another reason is that the cracks in the welded structures, like in the sheet metals, can cross a distance more than 1 kilometer per second. So it's like longer than actually the ship itself in 1 second. So you cannot observe the crack or the failure. It happens like in a millisecond. And in the lower temperatures, they like steel plates behave as if they were glass, so they just break. So against that failure, we have this rivet joints. Like if you have seen the Eiffel Tower in Paris, or I don't know if you have ever cruised in a ship, we all see those joints. So this is actually to avoid to avoid the crack to go further inside the plate, because when the plate is over and it comes to the joint, it just stops and cannot continue with the other plate. So these are mostly used, but it takes it takes longer time to build a ship in that way compared to the all welded ships. So I think all of us know the Titanic disaster. Like it's we know the movie, but we mostly know about the Kate Winslet and Leonardo DiCaprio like having a romantic trip, and it ends up in a failure. But there's actually a hidden truth behind the thing. So I want to show you the video. Should I say yes? Yeah.
As history progressed, builders of ever more complex systems and machines were discovering the more complex the system, the more things there are to go wrong.
The Titanic, I think, is one of the most classic illustrations of that. Had just any number of things, just one thing been different, the disaster wouldn't have happened.
She was the biggest, the most luxurious, the most expensive. Millionaires used their influence to get tickets on her maiden voyage from Southampton to New York. Then, at 11:40 p.m., the fifth day out, she struck an iceberg. 1,507 souls went down to the bottom. That the total area of the holes in her side were only about the size of a refrigerator. What happened to sink the unsinkable ship?
The killer is when the top of the bulkhead goes below the waterline, that allows the next bulkhead in the cascade to be flooded. See, so what happens, as soon as the weight of the front pulls the top of the next bulkhead below the waterline, and the water can cascade into the following bulkheads.
That's the mechanical cause of the disaster. But mystery still remains. How did the iceberg rip through the double steel bomb?
Not very tough steel. There's no question the plate in the Titanic could not be used in the ship today. But we do see linear indications that look like the seams failed. Bad rivets or bad steel. We pulled up a couple rivets. They don't look very good. So the rivets weren't very good, and the hull plate was not very good.
The steel of the Titanic's hull was far inferior to modern steel in one crucial respect. Because of its high sulfur content, it became brittle as it got colder. I've seen North Atlantic, the Titanic's hull was more prone to breaking rather than bending. And new studies indicate that 3 million rivets that held the ship together were made badly even by the standards of the time. Whole seams zipped open when she hit the iceberg. It's hard to imagine the most luxurious ship ever built. But underneath the gold leaf and mahogany, they used bad steel and poor rivets to hold it together.
Yeah, as it said, so there were so many other omissions that there are also like more detailed videos in YouTube if you're interested in this topic. But yeah, the steel, it was like it was a very cold water that they were operating the Titanic, so it got very brittle, and maybe a normal ship would be able to survive after that crash into the iceberg. Some more technical details. The first is the neutral axis. The neutral axis is the axis in the cross section of the beam or shaft along which there are no longitudinal stresses or strains, as we can see there. So this is actually like the boundary between the structure has tension and compression on the material. And neutral axis of the beam on the picture on the D, it shows the steel with fixed with the rivet and the rivet, and the E is the welded one. So the neutral axis occurs at the center of the area, or like gravity of the cross section of the beam, and the material close to the neutral axis contributes like little to the strength of the beam. And neutral axis of the hull, we can see the picture of the ship, like we had this definitions before. So we have port, stern, starboard, bow, and as you are going forward in the ship, we call it forward, and as you are going backward, you call it aft. So there are actually structural parts that contribute or not contribute to the strength of the hull. The first ones are the contributing ones. If a member is running continuously through the hull, it is contributing to the strength. But if it's not continuous, then it cannot actually contribute to the strength of the material. So yeah, all framing members that run transversely and all longitudinal members that are discontinuous, that cannot contribute to the strength. And the bending stress, like for the mathematical formulas, we know from the mechanics courses probably, to calculate the maximum bending stress, we just divide the maximum moment to the section modulus, and we get the maximum stress, and the maximum stress is inversely proportional to the sectional modulus because of the formula, and proportional to the bending moment. And the I stands for the moment of inertia, and for different structures we have different values for moment of inertia. The Hall Gilder, as Mutahar actually mentioned before, like I also had to think in my part, the longitudinal strength of Hall is based on the Hall's midship section. We can see the midship section on the left, and the vertical column, the horizontal column is the girder, and the vertical ones are the stiffeners. And the huge plate is actually the Hall. And girders, as I said, the horizontal ones are actually supporting the stiffeners to carry the transverse forces from the plating, from the outer plates. And for the section modulus, like the moment of inertia, the procedure is actually 3 steps to assess the overall strength of the whole girder. First, we have to find the neutral axis. Then we have to solve it for the moment of inertia. And then, as we know the moments, we can just divide it. Like we can find the sectional modulus by using the formula I showed in the slide before. In this case, there is something important because we only have to assess the materials that are contributing to the whole strength. And I have another video, a short one, which is actually a ship crash collision simulator. This is quite dramatic. So, okay, this is what actually happens after a ship collides into something. This is the midsection of the ship when we have the brittle fraction, which is like self-destruction. And for the maximum bending moment, this is actually the worst case combination of loads pushing down on the hull and buoyant support pushing up. And there's actually another procedure to find it. So we just draw a curve that shows the weight per foot, like the distance, of the fully loaded ship, the loaded ship. And then we create an imaginary wave of length equal to the ship. Then we compute the draft and trim conditions, and they have to be in an equilibrium. And then we can compute the bending moment for the given conditions, and it has the shape of those curves, like the way and the buoyancy. And again about the maximum bending moment, it is actually a 3-segment envelope, which is hogging and sagging at the same time. So it is like an envelope shape. And the maximum moments, as we mentioned before, are mostly, and they actually occur in the midship because it's the middle section that we have. The forces are from the bow and the stern. So they just they create the biggest moment in the midship section. And the maximum stress, actually it's It's basically the same with the maximum moment and the section modulus. We just divide it to find the maximum stress. And then, as they are actually designed with ships, like this is not sufficient because they still have the safety factor, so that they can be like sure that the ship is going to survive after bigger moments that it exerts to the ship. And yeah, the estimated maximum stress is designed to be well below the whole material's yield strength, so that they can be sure that the ship is not going to capsize or ground it. These are my references. If you have any questions,